the last topic before the AP exam. This is the last thing that I think that they're going to want you to talk about here. So here we go. When we did conservation of angular momentum in previous videos, we had a couple of situations, right? So far, conservation of angular momentum. We've now talked about collisions, actually not collisions, but objects that change shape as they rotate, okay? We talked about point masses colliding in specific places with an object that is externally constrained. Okay, so that's, for example, the kid jumping on or off merry-go-round. The merry-go-round is held in place. That could also be something like, here I have a bar that's hanging down and a bullet shoots into the bar. What's going to happen to the bar? Let's say the bullet embeds in the bar, and then the bullet and the bar rise up. That would be a conservation of angular momentum there, and that's a conservation of energy problem, right? This thing is externally constrained because there's a pivot point there. But sometimes things collide when they are not externally constrained, and that's what I want to talk about today. Let's say I have, nice clean scenario here. Let's say that I have a stick, okay? And our stick has a mass of m and a length of L, right? And let's say that there is someone holding the stick there, right? This is a person. So our person, P, has a mass of P, let's say the mass of the person is 5m. And for the point of this, we're going to treat the person as a point mass at the end of the stick, okay? Actually, let's make this more interesting. That's going to be person 1, and we'll have person 2. And mass of person 2 is 4m, and we're going to treat them as a point mass, and they're holding the other end of the stick. And let's say person 1 and person 2, I can't see the 1s and 2s, the 1 and 2, let's say they're ice skaters. They're ice skaters holding a stick on a pond. So there's no friction between the ice skaters and the ground. And let's say we have another ice skater. And let's say ice skater 3, we'll put them here, is going along, they're totally out of control, and they are moving along with the speed of v initial. And let's say the mass of person 3 is equal to, I don't know, just for sake of argument, we'll say 5m. Okay? And person 3 is going to crash directly into person 2. So what happens when person 3 crashes directly into person 2? Well, let's say these two people are not moving initially. So what's going to happen here is this system, when they crash, is going to rotate. And I think that makes sense that it's going to rotate like this, clockwise. But some other things are going to happen as well. So this is clearly a conservation of angular momentum problem. How do I know? The net external torque here is going to be equal to 0 because there's going to be a torque of 3 on 2 and 2 on 3. Those are going to be internal to the system. But the question here is, what is the pivot point? Right? If person 1 was like, on dry ground or like holding on to something, so they were an external constraint, this problem would be very, very different. But the pivot point here, in the absence of an external constraint, is the center of mass of the system. Now, here's the trick of this. What you have to imagine is the center of the mass after the collision, not before the collision. So like once 3 has become part of the system with 2, we need to know where the center of mass is because that's the point about which this system will rotate. So let's do this. So I'm going to do a center of mass problem. I'm going to declare this to be 0, 0, and up is positive. Okay, and so we'll call it a y center of mass just so we know where it is. So y com is equal to the sum of the y-m's over the sum of the m's. By the way, let's just back up. Why is it the center of mass? Remember we said that nature seeks to minimize energy. And kinetic energy rotationally is 1/2 I omega squared. So of all the things rotating at omega, the one with the smallest I has the smallest KE, right? And so if a system is going to rotate at omega, it's going to do so at the smallest moment of inertia. It's the action. The principle of least action is actually the underlying notion of that that nature tends to seek lowest energy states. So I is minimized when the distribution about the center of mass, or rather the distribution about when the axis is rotating about the center of mass, because that minimizes the distribution of the mass about the center of mass. Sorry, it was a little wordy, but we've gone through that argument before. So mass 1, which we said is here, is 5m times 0 plus the stick here, so that's going to be m times L over 2, because that's where the stick center of mass would be, plus mass 2, person 2, which is 4m times L, and then the next person, 5m times L. Okay? Because this person would be attached there. And this is over 5m plus m plus 4m plus 5m. So what do we have on top? We have, all right, just allow me to make the mass of the stick 2m. Just gonna make this math so much easier. I'm cooking this problem so that it comes out to be something nice. Trust me, I usually do the same for you when I make problems. So let's just do that, because that makes this ml plus 4ml plus 5ml all over 15 ml, which is 2/3 L, meaning this is going to be right there, 2/3 L up from here, where the center of mass of the system is, and therefore where the axis of rotation is. So why is that important? Well, when I go to do L initial of the system is equal to L final of the system, what is the, let's do a declaration as well. This way, and this way, and this way are positive, right? Why is that important? Well, the initial angular momentum of the system comes from this object moving linearly, and so I want to know what the lever arm distance for that is. And if I draw in this VI's line of action, I can see that that lever arm distance is 1/3 L now. But until I knew where the pivot is, I wouldn't have known what the lever arm distance was. So here, this is the initial angular momentum of object 3 is going to equal L final for the whole system. Or I should just go net external torque is equal to 0 here. So I'm going to do my MV L perpendicular term. And so that's going to be 5m VI, and the L perpendicular term here is 1/3 L. Now, remember with the MV L perpendicular, I need to impose directionality on that term. It doesn't have an omega in it that naturally brings in this in. I can do that directionality if we want to be really formal with doing this as R cross P, but I don't want to do that. That's not good for problem solving. This thing would make the object rotate clockwise. That's positive, so I'm going to put the positive there. That is imposed, is equal to I. So that's I of the system now. So what is that? Well, that's I of the stick plus I of the combined 2-3 mass plus I of 1 omega final, right? A little bit of a pain in the ass, but there it is. So let's do it. So I've got 5/3 MVI L is equal to I of the stick, 1/12. The mass of the stick is 2m the length of the stick is L squared. But I have to do a shifting factor because I'm not rotating it about the center of mass. So what is that shifting factor? Well, mass of the stick is 2m, and let's go back here. Our d goes from 1/2 L up to 2/3 L, so 2/3 L minus 1/2 L. That's 4/6 and 3/6, so it's 1/6 L. Okay, great. So 1/6 L squared. These do get nasty, by the way. If you noticed, it's kind of hard for them to be nice. So here we go. The combined mass of 2, 3, they've stuck together. What do we say? 2 is 4m, 3, so this is 9m, and it's 9m at, well, when they rotate, it's at 1/3 L squared, plus, and I'm just going to go down here because I want to save some space. We have mass 1, which is 5m, and that's at 2/3 L quantity squared, and all that times omega final. So let's just do the nasty problem here. Okay, let's see. So this first term ends up being 1/6 ml squared. So 1/18 ml squared. That's just ml squared. That's nice, right? Because 1/9 there, perfect. So at least some of the math came out not terrible. So this is 29 ml squared. Then he spoke. Okay, make a final. Let's try and get some sort of overall fraction. Oh, 18s. That's not actually too terrible. Look at that. So 3/18. Well, actually, let's just pull out an ml squared from this. 5/3 mvil. So things are going to cancel. I've got a 6, which is 3/18 plus 1/18 plus 18/18 plus 40/18 omega final. So m and m, one of the l's, one of the l's, and then I've got 4/18, so it's 22 62/18. So 5/3 vi is equal to L times 62/18, weird numbers, omega final. Let's just clean this up, 3 and 3, so that becomes 6. I can take a 2 out of that, so 3 and 31. I don't think I can get any further down than that. So 15/31 vi over L is equal to omega final, and there you go. That object rotates. So, a couple things on that. Notice, if object 2 were to have landed somewhere different, everything would have changed, right? Like, for example, if object 2 had gone along and hit object 1 there, this calculation would absolutely be different. The center of mass position would be different. And by the way, notice that the person with ice skating there would have caused an initial counterclockwise rotation. So the location that this hits not only determines this, but also determines whether this would give a positive or a negative moment of inertia, positive or negative angular momentum, and what the size of the angular momentum, because every single one of those distance terms would have changed based on where that object hits. And that's what makes these problems so interesting. Now, a second thing, and I'm just going to do it down here. Not only is angular momentum conserved, but linear momentum is conserved. Why? Because it's ice skaters. There's no external constraint on this thing. So not only is this system going to rotate, but it is going to translate. We're going to talk about what the it there is in a moment. So let's just do Pi cis is equal to Pf cis because the net external force is equal to 0. Great, so here we go. That's going to be 5m times vi. And then what's the final mass of the system? It's just everything. We know that's 15m vf, right? And so what is that? Well, that's 1/3 vi is equal to vf. But what is that the vf of? And hopefully you said the center of mass of the system, because this point translates, right, at a constant speed of 1/3 vi, even as the system rotates about that point. So this system will rotate about its center of mass, and the center of mass will translate at that speed. And that's what makes these problems so interesting. Now here, energy is not conserved. Why? Because when 3 crashes on 2, the force of interaction of 2 and 3 and 3 and 2, that's a normal force. Normal forces are non-conservative, and therefore there's work done by non-conservative forces. So no bueno on that. So I'm only conserving angular momentum and linear momentum, but not energy. If 3 had a big spring and bounced off 2, I could also conserve energy, and that would get even soupier than what we have because 3 wouldn't have attached to this, so the center of mass of this system would look very different because you have to think about what's the center of mass of what will rotate after the collision. That's this calculation, which then determines what happens with this calculation and what has terms here. So that is the last problem, is collisions between free objects. Lots of really interesting things that can be done with this calculation.